Okay, let's begin.
I think this is, yeah. So I think this is like the square.
So,
It's hard to articulate like why
last time,
sense of an average.
I
Also, I think 45% is almost
we learned about a new kind of Markov chain, an absorbing Markov chain, and something called an absorbing state. So, just want to make sure you know how to do some of those problems involving that. So, I guess let's just jump into it.
I think we did one of our answers.
So, this is from the rando problem set. So, the review for the next test, which you have on Thursday, was posted last week. I gave you 2 practice tests, as well as just a set of another set of problems. This is just an excerpt from that for you to practice. So, let's just make sure we're all clear on how to do some of these. Problem 1. So we're given a transition matrix. And we're asked to find the stationary matrix. By the way, it says here, solve the equation SP equals S to find the stationary matrix. I wouldn't tell you that. So I'd probably just ask you to find the stationary matrix. I expect you to know what equation you need to solve in order to do that. Just a heads up. Find the stationary matrix and the limiting matrix. And yeah, they kind of gave you the answer here. So your stationary matrix, remember, it is just going to be a row matrix. That is a distribution of probabilities for what you would be in state 1 versus state 2. This is state 1, state 2, the new state 1, the new state 2. And so, yeah, we want SP equals S. Well, this would mean that XY times 0.5, 0.5, 0.6, 0.4 is equal to XY. You do matrix multiplication on this side, so it's 0.5x plus 0.5y equals and then over here we have 0.5x plus 0.4y equals xy. And so you would get 0.5x plus 0.5y is equal to x. You'd also get 0.5x plus 0.4y is equal to y. Where's the 0.6 here? What's this 0.6 here? Which means from this one I can subtract x from both sides. I get minus 0.5x plus 0.6y equals 0. And I would take this as my equation 1. Remember that the second one is just going to give you pretty much the same equation. So the next equation I would set up is x plus y equals 0. So that's the system you have to solve. Because these guys are, not 0, 1. Because these guys are probabilities, they represent all possible situations. And so the sum of the probabilities must be 1, and from one of these equations I can get this. So now I just need to solve that. I can, in fact, multiply the top equation by, say, 10. And the bottom equation would be this, and I just need to solve that. So it's 1, 1, 1. Then here I can just take, say, 5 row 2 plus row 1. 5 times this plus that is 0. 5 times this plus that, 11. 5 times this plus that, 5. And so I would get that my y is equal to 5 over 11. And I would also get that my x is equal to 1 minus y, which is 11 over 11 minus 5 over 11, so that's 6 over 11. So ultimately, this means that our stationary matrix, which we usually put a bar over, is going to look like 6 over 11 and 5 over 11. This means, what is that guy going to look like? Meaning if you keep multiplying the key by itself over and over and over again, what does it move towards? Which group did this one? Group 1? What is this guy?
6 over 11, 5 over 11, 6 over 11, 5 over 11.
Right, it's just going to repeat the stationary matrix in each row. So if you keep multiplying this matrix by itself over and over and over and over and over and over and over, and over it'll actually approach this. Yep, so that's problem 1. So you should know how to find stationary matrices. Pretty much you set up this kind of equation. You're going to get 2 equations from actually setting each component equal to each other. You can ignore one of them because they're actually going to give you the same thing. One is just going to be the negative of the other one. And so for your second equation, you always use the fact that the x and y must sum to 1 because they are probabilities. That being said, you can solve that new system for the stationary matrix. You know that exists if any power p has only non-zero terms. And once you find the stationary matrix, you also know what will happen to the transition matrix if you keep multiplying it by itself over and over and over. Yes?
On the test, can we use any method we want to solve a system? Do we have to use a
Sure.
matrix? Okay.
Yeah. So that was wrong one.
Wait,
Did you guys actually get that?
Yes.
Yeah.
Yeah.
Wait, so why can you set equals to 0? The point of x plus 0.6y equals x. Why can you say?
Oh, I literally just subtracted x from both sides. I just brought all the variables to one side.
Oh, okay.
Yeah.
Oh,
Yeah, I literally just moved that x over.
yeah, okay.
And the thing is, if I went down here and I moved the y over, I would have get 0.5x minus 0.6y equals 0, which is actually just the negative of this.
Yeah.
So it wouldn't actually help you. So once you get one of them, just use one of them with this equation. That gives you the system you need. You had a question?
Yeah, I'm just saying, sorry, but how do we manage to get the limiting matrix again?
Oh, we had a theorem that says the limiting transition matrix is just going to be, every row is going to be this guy.
Oh.
You just line those guys up. Yes, that was a theorem that we did last time. So the next problem was problem 6. An important kind of problem. So it's a word problem. They gave us also a transition matrix. 0.7, 0.3, 0.4, 0.6. So these are the people who go by transit and the people who travel by car. Transit and by car. So 70% of the people who travel by transit in 1 month will also travel by transit the next month, while 30% of them will switch to traveling by car. 40% of them who travel by car will travel by transit the next month, and 60% of them will continue to travel by car. That's how you read that. Okay, so a new rapid transit system just started operating. In the first month of operation, it's found that 45% of commuters are using the system, 55% still travel by car. The following transition matrix was determined from other transit systems. What is the initial state matrix? What did you guys get for this? Right, that's from the sentence that says 45 commuters are using the system. So you're using state 1 is they use transit, state 2 is they use cars. So this is the transit probability and the car probability. That's the initial in the first month. B, what percentage of commuters will be using the new system after 1 month?
53.5.
How did you get that?
We multiplied what we had in A
Right, so you want the state after one more step. That's going to be the first state times that, which is going to be 0.45 times 0.55 times 0.7, 0.3, 0.4, 0.6. And that is going to be 0.45 times 0.7 plus 0.55 times 0.4. 0.45 times 0.3 plus 0.55 times 0.6. The first entry was what?
0.535 and 0.465.
And so these are the transit people after 1 month. These are the car people after 1 month. And so B, what percentage of commuters will be traveling using the new system after 1 month? 53.5%. So for B, the answer is 53.5%. What about after 2 months?
56.05%.
So you would find S3, which is going to be S2 times P, which is going to be 0.535, 0.465 times 0.7, 0.3, 0.4, 0.6. And so it's this row times column, and then row times column. And what was the number you get?
0.605 and 0.4395.
And so the answer here would be 60.5%.
It was 56.05.
What?
It's 0.565.
Oh, okay. 0.5605. So 56.05%. And by the way, the file that I uploaded has the answers at the end of the document, so you can go and check over this, check over your work. So, but you need to know how to get there, because I will be grading you for writing out your steps, so you should be able to actually express what you're doing, and you'll do it like this. Is that done? No. Find the percentage of the commuters using each type of transportation after it has been in service for a long time. What is that talking about?
The same thing we did before.
Right. So C is actually asking you to find the stationary matrix. So pretty much you're going to have x times y times 0.7, 0.3, 0.4, 0.6 equals x times y. This basically means 0.7x plus 0.4y equals x, and 0.4x plus 0.3y 7 and 4, 0.3x, 0.6y equals y. This one, I can subtract x from both sides, minus 0.3x plus 0.4y equals 0. And then I can just set x plus y equals 1. So I need to solve this system. And so I would have minus 3, 4, 0, 1, 1, 1. Row 2 plus row 1. So this means your y is going to be 1/7, and which means your x is going to be 6/7. So what is this as decimal?
That's not what we got. Yeah, it's 3 sevens.
3 times, oh, that should be a 3. which means this is a 4.
That's
The 4 sevenths
57.14%. Yeah. And then the next part is 42.86%.
And yeah, so the answer here. Okay, so how many people using transit in long term? Transit long term is going to be the X, 57.14%, and car long term. So if they just keep running this transit system, here's how they can expect things to shake out. The transit system will end up serving 57% of the population, while about 43% of the population will be using cars. Okay. So that's problem 6. Okay. Moving on to problem 8. That was 6 part C. Moving on to problem 8. We're given a matrix. So P is 0.4, 0.3, 0.1, 0.2, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 0, 1. This is A, B, C, D. A, B, C, D. So someone asked me, I don't think it was from this class, but I might as well mention it. When it comes to Markov chains, there are a few problems in the packet where you have to do 3x3s and 4x4s. 3x3s, it's good to remind yourself how to do with 3x3 matrices, because in like a week plus, you'll have to do it on the final. But computationally speaking, I'm not going to ask you to actually calculate anything with a Markov chain that's a 3x3 on the exam. But I might ask a question like this. I might give you something that's larger than a 2x2, but just ask you about certain properties of it, like which ones are the absorbing states. Okay, so remember what an absorbing state is. It's a state that once you enter it, you will never actually leave that state. And you'll notice C is going to map to itself 100% of the time, which means once you enter C, you will actually never leave C. Similarly, D goes to D 100% of the time. So once you enter state D, you will never actually leave state D. C and D are the absorbing states. It didn't ask this, but is it an absorbing chain? How do you know? So you could actually draw the picture here, just to illustrate what I'm thinking. C, D. A actually maps to everything. It even maps to itself. B will actually only go to C, and C would only go to itself, and D would only go to itself. So what does it mean to be an absorbing chain? Well, it means that you can get from any non-absorbing state to any absorbing state. So notice this is not an absorbing chain. So for example, how I know it's not an absorbing chain, there is no path from B to D, for example. Right? B is not an absorbing state, but D is. You have to get from any non-absorbing state to any absorbing state in an absorbing chain. So because there's no way to get from B to the absorbing state D, it's not an absorbing chain. Right? So you should be able to travel from any non-absorbing state to an absorbing state in an absorbing chain. So just because there's the presence of absorbing states doesn't mean that the system overall is considered absorbing. Let's see here, 9. Identify the absorbing states for the diagram and determine whether it represents an absorbing chain. So here we have A, we have B, we have C. A goes to B, 0.7, A goes to itself, 0.3. B goes to, no, C goes to B, 0.7. B only goes to itself with 1. And C goes to itself, 0.3. Absorbing state. Are there any? B is an absorbing state. Is it an absorbing chain? It is an absorbing chain. And here, we know it's an absorbing chain because B is the only absorbing state. I should be able to get from any non-absorbing state to the absorbing state. And since both A and C travel to B, it's an absorbing chain. So one thing, last class I told you about a very, I think it's cool, but a cool application of Markov chains that you guys use every day and probably didn't know about it, but the Google search engine, that's why it's so awesome compared to any other search engine, because it uses Markov chains. What you'll notice is that the internet it's actually an absorbing chain. Like a situation like this couldn't happen on the internet. So it's kind of why you need to know about these situations, because there are sometimes certain applications just won't apply. This is like saying there's some website out there that you can only get to it one way, and once you go to that website, you'll never leave that website because it's so awesome. Like, that's not realistic. So something like that couldn't really exist. So when Google was coming up with their method for the search engine, they realized that, you know what, we don't really have to concern ourselves with a situation like this. You just have to figure out the other situations and, you know, optimize your programming to fix that. 14. Okay, a manufacturer obtains clock radios from 3 different subcontractors. So it gets 40% of radios come from A, 20% of clock radios come from B, 40% of clock radios come from C. The defective rates, 1% of things that come from A are actually defective, which means 1% of the radios that they buy from this manufacturer are defective. And here, 5% are defective. And from C, 2% defective. I didn't just do that from the beginning. So that's the situation. So a defective clock radio is returned by a customer. What is the probability that it came from A, B, or C? And I think we have to do from A or B. So how did you do this one? What group worked on this? How did you actually figure it out?
We did the probability of A given it's defective. So then.
Right, so 14A, what is the probability that it came from A? So you're asking for, what is the probability that given we know it's defective, what is the probability it came from A?
So then we did 0.4 times 0.01 divided by 0.4 times 0.01 plus 0.4 times 0.02 plus 0.2 times 0.05.
Okay, what did you use to figure that out?
I forget the name of it, but it's the probability of
Yeah,
A
it's,
and
it's
B.
Bayes'
over-
theorem, so
okay.
that's very important. The name, I don't know what it's called, but I know how to do it. You'd survive, you'd get 100% here for that. But Bayes' theorem is how we do this. So this is going to be the probability. Notice what the probabilities that we were given. What this guy is saying is, if it comes from A, there's a 1% chance it's going to be defective. And this says if it came from B, the probability it's defective given that it came from B, well, that's a 5% chance. And then here, if it came from C, there's a probability of 2% that it would be defective. And so we're given a bunch of conditional probabilities in the opposite order of one we want. Bayes' theorem should be the kind of obvious go-to here. We want A given D, but I only know about D given A, and I know about D given all the other stuff. So according to Bayes' theorem, this will be the probability of D given A times the probability of A divided by probability of D given A times the probability of A plus the probability of defective given B, probability of B, plus the probability of defective given C times probability of C. So that's 0.01 times 0.4 divided by 0.01 times 0.4 plus 0.05 times 0.2 plus 0.02 times 0.4. And that was what?
0.182.
And of course, for part B, it is similar. Part B is similar. What was the probability that given that it was defective, it came from B? Well, that's just going to be the probability of D given B times the probability of B over the probability D given B times the probability of B. I mean, this one question asks you about all of them, but of course I would only ask you one of these questions. D given A times the probability of A plus probability of D given C times the probability of C. And so this one is going to be 0.05 over 0.2 divided by pretty much the same denominator from this one. It's going to be the same denominator. 0.05 times 0.2 plus 0.01 times 0.4 plus 0.02 times 0.4. And that one is what?
45.45%.
45.45%. And this one was 18.2%. And that's that. So, any questions on that? Yeah, so this wasn't a Markov chain problem, just threw one in there. And in this packet there are other problems too. There's stuff to deal with expected value and some other stuff, I think. Just the rando packet covers a lot of the stuff that we did towards the end, to make sure that you guys can get practice. So you guys should practice from the rest of them, practice from the practice tests that are online, and that should put you in pretty good shape for Thursday. Any questions? Yeah, so Thursday we just have the test. It'll last about an hour, so you'll be let out 15 minutes early, but that's it, we're done. We're out of here. Okay? Go steady, get home safe, stay warm, and Thank Markov chain for Google.
I thought the
See
same.
you guys on Thursday.
I'm shipping you out.